This problem, first of all, I want you guys to draw a picture to describe the context of the problem, right? In the main concourse of the local arena, there are several viewing screens that are available to watch so that you do not miss any of the action on the ice. Okay, so basically I would put an E in here. This one is for the eye level of the viewers, and on the screen I'm gonna highlight it in yellow. There are a couple of like screens in here, right? And based on the description of the problem, the screen is 7 feet away from the viewers. So this is 7 feet away from the viewers. Okay. And then the bottom of the one screen is 3 feet above eye level. So this little difference in here, this little height in here, it would be 3 feet above the eye level. And on the screen itself, the yellow one is 7 feet high. So from here to here is 7 feet high. Okay. And then the angle of vision inclination is formed by looking at both top and bottom of the screen. So top of the screen, bottom of the screen, they would create this angle, right? And this angle, let's just give it a name. Let's call it theta for the angle, right? And then we have to find that angle of vision, which is theta. All right, so the plan in here is that we're going to put everything in right triangles. So I'm going to look at the biggest right triangle that I'm having in here, which includes the angle E, right? And then in order to get the angle theta, my plan is that I'm going to get the angle E first. And then after that, I'm going to get the value of angle X, which is the angle within the smaller right triangle in here. I'm going to call it X. And then if I minus X from E, I'm going to get the value of the angle theta, which is what the problem wants. Okay, so let's do that. To get the angle E, first of all, let's look at the big right triangle, where the height in here would be together 10 feet. And that would be the opposite side to the angle E. And the 7 feet in here, it would be the adjacent side to the angle E, right? So SOH, let me just put up the definition in here. I have SOH. And based on the description of the problem, I have O and A, so I'm going to do TOA, right? So tangent of the angle E equals opposite divided by adjacent, meaning 10 feet divided by 7 feet, okay? And in order to get the angle E by itself, I would have to do the inverse function. What it does is that I'm going to swap the roles of the output and the input in here. So I go E, the angle E, it equals to tangent inverse of 10/7. And that would be what I'm going to put in the calculator, right? And make sure that your calculator mode is on degree system, okay? Then you're going to get the angle E approximating to 55 degrees. Or if you want to be more precise, you can keep it to 4 decimal places as 55.0080 degrees. Like this, okay? So first thing done, for part done. Now let's get to the X angle. In order to do that, let's look at the smaller right triangle on the bottom in here, right? So 3 in here, it would be the opposite side to the angle X. And the 7 in here is one more time the adjacent angle to the angle X, right? So what we're going to do is that we're going to do the same step as we did before. We're going to use TOA because we have opposite and adjacent in here. And I'm going to go tangent of angle X this time equals opposite divided by adjacent, which is 3 divided by 7. And in order to get the X by itself, I'm going to do the same thing. X equals tangent inverse of 3/7. I'm swapping the roles of the angle and the value right here and here, right? And if you put it into the calculator, make sure it's in the degree mode, you're going to get an angle approximating to 23.1986 degrees, okay? And our last part in here, to get the angle of vision, which is theta, I'm going to do it in green. We just have to subtract them, right? We're going to get the big angle minus a smaller angle. Angle E, we know it equals to 55 degrees, or to be more precise, 55.0080 minus the x angle, which is 23.1986 degrees. And then the answer in here, it would equal to 31.8094 degrees. And this is it. We done.